next session, we're going to hear from two teams who are leading projects that are part of MIT's Climate Grand Challenges effort. This effort was started a few years ago, and in a way, it's a response to the question that Lindy asked earlier in this session about how do you connect people across MIT and kind of get people out of silos to work on big problems that defy disciplinary boundaries. And so over 100 teams across MIT pitched projects to this Climate Grand Challenges effort. Somewhere in the upper 20s were selected as semifinalists, and of those 5 flagship projects were green-lighted to go forward, and 2 are led by EAPS PIs in collaboration with colleagues across the Institute. And they're really exciting because they take the expertise in EAPS and connect it to big, important problems in society and to expertise across the Institute and beyond, as you'll hear in the presentations that follow. And so we're going to hear from the 2 projects, starting with Noelle Selin, the interim director of the Institute for Data Systems and Society here at MIT, with an appointment here in EAPS as well. So Noelle, I'll hand it to you.
Great. Well, thank you so much. I'll give you a brief introduction to our project, Bringing Computation to the Climate Challenge, which, as David said, is a large effort as part of the Grand Challenges program. And our aim is to bring the latest science together with computation from MIT together to make climate modeling better, more accurate, faster, and also more accessible. You'll hear from a small subset of our team today, but we're speaking on behalf of a much larger team. Our project spans multiple departments and schools at MIT, but notably, in particular, represents a strong partnership between faculty in EAPS and those in MIT's College of Computing, who have expertise in machine learning, AI, and other computational techniques. So why bring computation to the climate challenge? It's because of the key importance of climate modeling. Models are vitally important tools that help us understand the climate system. And these figures are from the Intergovernmental Panel on Climate Change, in which several EAPS faculty have participated and been involved in the past. Through climate models, scientists and decision makers can better understand how changes in temperature have evolved over time and what their causes are. On the left, this analysis shows how models can be used to help understand that it's human influence that has warmed the atmosphere. And the observed temperature, the black line, can only be reproduced in models when human emissions of greenhouse gases like carbon dioxide are included in those models. And the figure on the right shows how models can be used to project global temperature over time under different scenarios. Each of those colored lines represents a future scenario that's been run through a suite of different climate models. And there are 5 different scenarios presented here. And the spread here illustrates that these climate models have some uncertainty in the future climate under each scenario. And I'll come back to that point. So remember the 5 scenarios and that spread of uncertainty. So what do these climate models look like? They're very complex, increasingly high-resolution computational models. Each of these has thousands of lines, hundreds of thousands of lines of code. And they've been developed and enhanced and added to over roughly the time that EAPS has been around, for 4 or more decades. And the fundamentals of the physics and dynamics of these models builds really strongly on the work of early work of EAPS faculty to understand the climate system. And a great level of detail is really important to understand differences across the globe. But this isn't just a natural system, which is illustrated in the globe on the left. The globe on the right is a movie that includes aerosols, particles in the atmosphere that are mobilized in part by human activities. And if you look at what's those particles in white, that's sulfates. Those are emitted from human activities like burning coal. And the red and yellow are fires, and those are often initiated by human burning. So you'll get the point from these 2 graphs that in order to understand the system, we can't rely just on understanding the natural processes. We need to take into account the fact that human activities are both determining the Earth's temperature and the composition of Earth's atmosphere. MIT also has a long history of modeling the interactions with the human system. Here's a chart that represents the longstanding work of the MIT Joint Program on Science and Policy of Global Change. They've been looking at the interactions between human and Earth systems for over 3 decades, again, from the early days of EAPS. I'm showing a citation from 2 decades ago, but their updated work is accessible on their webpage. And we're working in close integration with scientists at the Global Change Joint Program within MIT's Center for Global Change Science on our Grand Challenge project. But this chart illustrates the challenge of trying to model everything. Models are really useful tools, but when you try to include more and more processes, they become more complex, more computationally intensive, and need increasingly specific expertise to run, and expertise from a broad variety of different fields. And this complexity is part of the reason why the early graph I showed included just 5 different scenarios of future human activities and emissions. It's a huge undertaking to run a climate model. Large numbers of model runs are typically needed, though, to get information on future risks. For example, the probabilities of the type of extreme events that the next group is going to talk about. But that takes both time and expertise, and that limits the number of alternative scenarios that can be run. But here's the problem. That means that those scenarios and their outputs aren't usually targeted to the specific needs of a user. And increasingly, in a world in which climate is determined by human activities and human choices, all of us need climate information across very different sectors, and that's needed to plan infrastructure, investment, and ensure climate resilience. So that's really where our project comes in. We're using the latest techniques from computation to first, in partnership with the CLIMA project, which my colleague, Professor Raffaele Ferrari, has spearheaded at MIT in partnership with Caltech to develop a new climate model, moving beyond those 40 years of legacy code to translate climate models into new computational language that's better designed for today's research and infrastructure. But for our BC3 project, using AI and machine learning and building on this effort, the core of our project is to bring those existing and the future state-of-the-art climate models literally into the hands of people that will use them. And our guiding principle is that it shouldn't require a PhD from EAPS to engage with climate modeling, and to be able to simulate scenarios of interest and engage with these tools and get useful and relevant results. But in order to implement this, we do need a cadre of PhDs from EAPS and beyond. So with that, to talk about some of our concrete steps, I'll introduce Dr. Andre Souza, who's a research scientist in EAPS, who'll tell us more about that approach.
Thank you for the introduction, Noelle. As mentioned, one of the goals of the BC3 project is to create tools that help people understand what the effects of climate change will be. Now, the best known tool that we have for understanding how the climate will change are Earth system models. But Earth system models require computational resources on the scale of what you see on the left. And you can see a person there for scale on how large these supercomputers are. And it's not just one of these computer racks that are necessary, it's hundreds of these. And hundreds of these that run simulation code for months. And that's how we get climate information. But we'd like to take that same kind of output and make it accessible on a laptop, roughly on the order of 10,000 times smaller computation, and run in a millisecond. Orders of magnitude difference between the Earth system model and what I'm going to talk about, which is an emulator. Building an emulator can be thought of as in a few different steps. And the first step is to first incorporate our domain knowledge of what we understand about the Earth system, in this case, what a potential human emission scenario is, and translate that into a number, such as globe mean surface temperature. This single number is, let's say, a quantitative assessment of how much warmer the Earth will be in the future. But the reason why we care so much about this number is that it correlates very strongly with what we experience on a local scale. So global information about what happens on the entire Earth is informative of what happens to us here in Cambridge. And using CMIP data, we can construct this pattern that you see on the right, which tells us, given the globe mean temperature, how much warmer do we expect certain regions of the globe to be. The red being warmer, the yellowish being, well, still warmer, but less so. So here we see that the poles are warmer than the equator. And this kind of technique, known as pattern scaling, brings global information to the local level, but still loses temporal information. But what we experience every day isn't just an average temperature over a year. just looking at the temperature today, we see it go through a range of values and possibilities. So we not only want to construct emulators that for a given emission scenario tell us what this global mean temperature is, but we'd like to understand how the ranges of potential temperatures change over time. In the top, what I'm showing is an average value, and then in the bottom three, I'm showing variability here in January, corresponding to the same global mean temperature increase. So we're not constructing just emulators that give us average values, but trying to create emulators that are constructed for our local experiences, given the best available science. And this is constructed from a CMIP class model. But not only global mean temperature, but also precipitation, understanding how much more rain or less rain we can expect. And here, a similar exercise has been done where, in addition to obtaining local information on the global scale, we can also emulate ranges of potential values and understand not just numbers, but distributions and likely scenarios that we'll experience in the future. And all this leveraging what we know from CMIP class models. These aren't the only class of emulators that we're constructing, and we're not just looking at temperature and precipitation. We're also constructing emulators for daily temperature maximum, how extreme we can expect extremes of the future to be given climate change. We're looking at incorporating more domain information, not just obtaining this single scalar value to inform our emulators from models, but understanding that the history of emissions also affects the kind of patterns that we'll see in the future due to the lifetimes of chemical species in the atmosphere. In addition, other classes of emulators, such as understanding how much heat gets absorbed to the ocean, understanding ocean acidification, are also classes of emulators that we're building. But we also haven't kept our head down and ignored the recent progress in AI. We've also looked at the technologies used to construct tools that we use, such as ChatGPT or DALL-E for creating images, and taking that same technology but repurposing them for the use of taking climate information and making them accessible to everybody in the world. And with that, to close the loop on how we obtain these emission scenarios in the first place, I'll hand it off to Chris to discuss how we can predict how humans will behave and what policy decisions affect.
Thanks, Andre. As my colleagues have done a great job highlighting, there are simply too many possible emission scenarios for us to assess really more than just a small handful of those scenarios using our state-of-the-art global climate models. Sorry, do I need to, I need to speak up a little bit and closer into the microphone. There are simply too many scenarios to assess. We can only do really a small handful of them using our state-of-the-art climate models. Now, our emulators pose a potential solution to this in terms of lowering computational complexity, but that still begs the question, even if we had a perfect climate emulator, how would we go about generating realistic emission scenarios? So as a first step towards answering this question, the BC3 program has partnered with Climate Interactive and has begun work integrating with their En-ROADS platform in order to close the loop and generate these realistic scenarios. Thank you, sorry about that. I'm sure many of you are familiar with En-ROADS and have heard it, as it was originally developed here at MIT, and it's now one of the most used platforms worldwide for facilitating a climate policy discussion. It's been used at the local, national, and even international level to facilitate these discussions. And as you can see here, it's been used by over 300,000 people around the world. Now, what makes En-ROADS so powerful is these policy sliders, which you can see here, which are a simple and intuitive way for users to specify these emissions profiles. So through this collaboration with En-ROADS, we're providing them with new capabilities, such as the temperature and precipitation maps that Andre showed, as well as having access to this tool that we can use to generate realistic emissions pathways. Now, I know this is focused on En-ROADS right now, but it's important to point out that the work we're doing is not particular to this platform or to any one platform. We are aiming to make tools and emulators which are as accessible to as many audiences as possible, and not only that, we want our tools to be as easy to integrate with other existing climate tools, such as those used for impact assessments. And with that, I'll turn it over to Glenn, who will be going through a brief demonstration of the work that we've been doing with respect to the En-ROADS platform.
Thank you. I'd like to just give a brief demonstration of coupling En-ROADS to one of our emulators and visualizing the results. The movie is running real time. The calculations every time the globe or the map changes are being done as you see them happening. The En-ROADS frame shows the baseline pattern if we don't do much. And on the right are the temperature anomalies at various parts of the globe. And the small map are the temperature anomalies in Cambridge, which you can see is somewhat higher than the global temperature change. Now, if we go up to En-ROADS and we start making choices, we cut coal, we cut oil, we cut natural gas, we plant a lot of forests, you can see we can then take that result, look at the whole emissions scenario, not just a particular time, but the whole time history. We paste it into the emulator, and the temperature changes, and you can see the temperature in Cambridge went down, temperature globally went down. But to make that more clear, we can look at the difference. How much better was it when we changed the scenario, when we made those changes? And you can see the temperature went down a little bit in Cambridge, but quite a lot elsewhere. As Andre mentioned, looking at different realizations can tell you quite a lot. Here, the temperature went down quite a bit more in Cambridge, but in a different realization, quite a bit less. So the typical variation, even in a monthly average that you might see, and we do see outside, is represented by these emulators. We can also show the precipitation. As you can see, it's rather higher around the equator. And if we go to Africa and zoom in, you can see there's quite a lot of variation, even over rather small distances between offshore and in the Angola, Congo, and down in South Africa, there's almost no change in precipitation. So by linking policy and mitigation efforts to global and local changes in various impacts, allowing exploration of the ranges and providing visualizations, we are producing a tool that we think will be useful for planning and helpful in climate change education and climate justice efforts. Thank you.
Okay, my name is Paul O'Gorman. I'm a professor in EAPS, and I'm one of the co-leads of another Climate Grand Challenge project, which is highlighted here, preparing for a new world of climate and weather extremes. And my co-leads are Kerry Emanuel and Miho Masaru, who I'm happy to see is here also. So the motivation for our project is really focused on extreme weather and climate events that already have a large impact on society. You can measure that, for example, in costs associated with these events. So these is time series you're seeing for the US of billion-dollar events. It's adjusted for inflation. There's a lot of changes going on. It's not just climate change. This is a complicated pattern, but these events are already having a big effect, and we think they'll have a bigger effect with climate change. And this is showing tropical cyclones, floods, and so on. It's actually leaving out severe convection, which we'll be touching on later, which is contributing a lot of the current billion-dollar events of these type. So to focus in on two events that really were, I think, shocking events in terms of the records they set, I'll show you. One is Hurricane Harvey on the left, which led to rainfall records in the US, and then the Western North America heat wave a couple of years ago that, again, really went beyond anything we had seen. So these events are really challenging for modeling. They're challenging for adaptation. And so these are the kind of events we would like to focus on. So our project has 3 parts then: climate modeling and risk assessment, adaptation for cities, and then addressing the effect of weather and climate extremes on the energy system. So the energy system's changing, we're moving to clean energy, but this interacts with the climate system, and we want to facilitate mitigation of more greenhouse gas emissions. A lot of what we're doing will apply globally, but we're focusing in on a few different places: Boston, Puerto Rico, Broward County, and South Africa. And so we're doing a lot of work in those particular areas. And this involves a lot of people across the Institute and plus NCAR. And some of the people involved are shown here. So I want to tell you about the specific challenges we're trying to address. And this is a big area, obviously. So one of them is that we just actually don't properly understand what's happening a lot of time to these extreme events. So I study extreme precipitation. And this is a graph showing for the US what the trends in extreme precipitation are over the past century. And we're here in the Northeast. You'll notice that's where the biggest trend upward has been. You may not have noticed that, but that's what's happened. And so why is that, right? Is that just unforced variability? Quite plausibly it is, but it also probably has some signal. The overall signal upward, of course, is related to climate change, we believe, but the pattern, why east versus west is so different, why is that? That's the kind of thing we need to know. We need to know results at the regional level in particular and understand what's going on. Will this continue, this pattern? So to address that, well, that slide is not quite right, I'm sure you can see, but we're addressing 2 parts. One is the, really hard to see, but yeah, the heat wave is shown again on the left, and we're looking at precipitation extremes, temperature extremes, and convective storms. Kerry will talk a little bit about the convective storms later. And then the second part is really going beyond extreme weather events and looking at what's the risk of extreme climate change, and that's work led by Dan Rothman and Dave McGee and others on using the past climate to inform what's the chance of tipping points, big disruptions to the carbon cycle, and so forth. So that's looking a bit longer term at what we're doing now. The big challenge there is to relate the past climate variations to scale them so that they're applicable to current climate change. Okay, I'm glad to see this slide is better. That's great. So the second objective is to go beyond understanding, but develop tools we can use to assess risk in particular locations. So we're doing work on modeling of cyclones, extratropical cyclones, tropical cyclones. We're also looking at downscaling. So a lot of the outputs we get from climate models are too coarse a scale to actually use directly for impacts assessment. So we'd like to use machine learning and other techniques to do a better job of getting them down to the relevant scale. And the third thing I'm highlighting here is rare event sampling, which I'm working with a postdoc, Justin Finkel, on this. And the idea there is to use kind of clever approaches that have been used in other fields to actually sample the rare events we're interested in more often. Just instead of just running a model a long time and seeing what comes out, actually bias things towards seeing more extreme events. And again, I'll talk about that a little bit more later. So I'm going to hand off to Miho, who's going to talk about adaptation for cities.
Sorry, Paul's a lot taller than I am. So. More? Okay, all right, can you hear me now? Okay. So I would like to talk a little bit about how all of this work from modeling and downscaling then comes and touches people and communities. And so we're really trying to understand how all of these cities that are really created by diverse communities, and they're operated through a range of different power dynamics and embedded histories, and adaptation's costly. The strategies we have now are extremely costly and extremely complex in different legislative overlays. And currently only those who have the time and resources to navigate these procedures can really figure out what the next steps are. So we're developing tools and design strategies to align otherwise top-down processes to engage with and foster bottom-up collaboration. So get right, okay, in front. Okay, working with emergency managers, city planners, real estate developers, and residents, we're creating more flexible and equitable ways to prepare for these extreme weather events. It's our role to listen and to learn while sharing new data and developing new tools that allow for co-creation and adaptation. So we're working closely with these partners in Boston, Broward County, next year, Puerto Rico and South Africa. And we're trying to find ways to integrate the specific needs of these stakeholders with the design of toolkits and flood modeling. So we're developing a number of different tools, but here are a few examples. One is the enhanced situational awareness. So taking a scenario that comes from our colleagues in EAPS, understanding where flooding is likely, but then emergency managers have asked us, well, we understand one scenario now, what happens when there's a change? Or what happens when we put flood barriers in one place and that pushes water elsewhere? Currently, it's very costly to get consultants to rerun these scenarios, and we're working on a way that this can be done much more quickly, and so that multiple scenarios can be driven. And then when the event does occur, we want to match this with ground truth data. And for this part, we're also helping Boston create a community emergency response team. Another tool is a preemptive planning tool for recovery, trying to figure out exactly what kind of scenarios will happen and then planning for that recovery. The recovery period is when a lot of the federal funding comes down, and for the most part, it's done in an ad hoc process. And so by understanding the extreme weather scenario, how we can plan for the future, really helps to do that now, and then it creates a more inclusive planning environment. And the third is working with real estate developers and figuring out other kinds of adaptation strategies that can really help communities adapt going forward. And now I'd like to hand it over to Kerry.
So I'll push the thing back up. I am going to hand it over to Kerry, but I first wanted to introduce a little bit more about one other aspect of our project, which relates to the energy system. So as I mentioned earlier, our energy system is rapidly changing and vulnerable to extreme weather events. So what we're trying to do is characterize and address vulnerabilities in this evolving energy system. So what's shown here is some work from Jessica Transek's group. And it's the storage state of charge for a wind and solar system. So you have wind and solar and you have essentially a battery attached to it. And you'll notice that at certain times, essentially there are these extreme events. Oops, that's the wrong button. Okay, extreme events indicated by the black triangles. And so those are basically periods of low wind and solar due to some kind of extreme weather pattern. And you might think, okay, what's that? Maybe the turbines shut down due to a cyclone. Actually, no, these are more like multi-week events where the weather pattern is such that there's more cloud, the wind is low, and so forth. So this brings up an entirely different type of weather system, and we'd like to understand that, understand how predictable it is, and so on. What does it mean for siting of turbines, for example? Okay, so lastly, we've a few research highlights to share involving EAPS researchers. So one of them is in the area of downscaling. This is work by postdoc Anamitra Saha and Sai Ravella, who many of you know. And the idea here is to go from what's regarded as low resolution. Actually, for us in climate modeling, we would often view this as not low resolution, but low resolution quarter degree. And then the idea is to go from that using local information to a much higher resolution field of precipitation in this case. And so one problem with doing this for extreme event is we don't have that much data to train on if you're using a machine learning approach. And so what was nice about this paper, which is just coming out now, is that they used kind of clever ways to leverage what data was available, and they also included physics in the form of orographic rainfall physics to take advantage of the topography data we have. So this is bringing together generative AI plus physics to do a better job on downscaling, really exciting. The second highlight I want to bring up is from Justin Finkel, who's a postdoc in EAPS, working with myself. And this is the rare event sampling idea. So this is used in physics and structural engineering and other fields. And we're trying to help bring this into climate science. So the idea is you want to, you have a simulation, for example, with a general circulation model. You want to study extreme events, but they don't happen very often. So what you do is you restart the simulations, as you can see on the left, prior to reaching some threshold, and you look for ensemble members that go to much higher values of whatever your target variable is. It could be temperature. And so that's called boosting, and that works pretty well. But that's not so useful if you can't also track the probabilities. So what's really cool about this work that Justin's doing is that he's also tracking the probabilities, and then you can get this kind of return level versus return period graph where you can go to much higher return levels or return periods for the same amount of computation. So that's really exciting. So now I will hand over to Kerry to present the last few slides.
There, okay. That's what this is really here for. I thought I had a slide before that, actually. Go back one if you can, or I don't know if I can. Nope, I guess they're in. All right, well, I'll start with that one. I don't know if the other one's there. So, a Cambridge politician, Tip O'Neill, famously said that all politics is local. And my own take on climate is that all climate is local in the same spirit. That is, climate we present as a global phenomenon, but the effects, the cumulative effects, are largely regional and local. And the problem we have in assessing climate risk, which is absolutely essential as a precondition for doing something about it, is that the events that cause the most damage over the long run are relatively rare. Across many, many geophysical phenomena, it's the 1% annual probability, roughly, events that cumulatively do the most damage. If it's rarer than that, there are not enough of them. If it's more common, we're adapted to them. The problem with a 1% event is you need about 500 years of historical data in a stable climate to get that robustly, and we don't have 500 years. So even if we didn't have climate change, we have to do a much better job bringing physics and other techniques that you heard from Paul and Miho to bear on this problem. And so among the phenomena that we need to understand that don't come directly from climate models are severe thunderstorms, which cause a lot of damage through hail, mostly, actually also tornadoes, flash floods. And at the point here, we don't really know how to explain the current observed spatial distribution of these events around the world. That's how far behind we are in that phenomenon. And I just wanted to say with this slide, this is a slide that's only been made possible by work that's been done in another department here, civil engineering, MIT, that you couldn't have seen 5 or 10 years ago. It's a climatology of soil moisture from space. And why am I showing you that when I'm talking about severe thunderstorms? It turns out that to understand the physics of how these storms develop, you need to understand the physics of soil and vegetation, and that's a relatively recent realization. So it's a baby step on the way to being able to quantify the risk and how it might change with climate. And I'll just quickly end with this. And that is that another big phenomenon I've worked on over many years is hurricanes. And we don't have nearly enough historical record to even get a handle on past risk, and those underlying statistics are changing. So we have to figure out, or we have, I think, to a large degree, figured out how to bring physical understanding of the kind we teach and do research on in this department to bear on generating or downscaling very, very large numbers of these events in current and future climates from climate models. And finally, to turn that into useful information by marrying the hazard risk with exposure, which is what we get from economists, where's the value, and how vulnerable that infrastructure is to damage, which we get from the engineers. So this is why we span across many departments, and it's my quick take on that. Okay, and I'm just going to finish up with that this is really what I was trying to say before, is that I talked about this morning about why we had to bring disparate disciplines together to really understand climate across the whole department and some other departments. Now we're taking even a bigger step forward here, which I think is very exciting, which is to take our understanding of these the geophysical risks, natural hazards, and by marrying them with economic data and engineering data, pardon me, that tells us how vulnerable various structures are to various kinds of events like wind and water, will we be able to finally give some numbers that are useful to society at very high granularity, right down to the house you own, I hope, and think will happen. Actually, it is happening. So it's a very exciting time to be doing this, and I'm really happy to be part of this team. Thank you.
Okay, now we'd like to invite representatives from each of the teams up here and we'll invite questions from the audience. So think of your questions as folks come up. All right, there's already a question back here. Carrie, can you come up as well? And Miho. All right, go ahead, John.
So the question I have is one that's been on my mind for a while, and it's probably unfair to ask to all of you folks, but there's people here who would know. We can expect disasters, floods and storms in the next decades. How has the Mogollon building been designed to address the fact that there's going to be disasters?
Carrie, you've been thinking about flood risk on the MIT campus, so.
It's true that it's interesting that after we got finished doing a study for Bangladesh on flooding, we said, what about the MIT campus? And so there's a lot, we put together some years ago, a team of very good people across many disciplines to look at MIT's flood risk. And they're making very good progress on that, but it's substantial. It turns out MIT has a lot of infrastructure that's under the current level of the Charles River, including the control room for our nuclear reactor. So I don't see a mass exodus. That's a good sign.
Other questions? Tom, and then I think, is there a question over here after that? Okay, great.
As I'm just curious, with the emulators and et cetera, which are taking AI, how do you handle the fact that they might get it wrong and someone's basing their policy decisions on this rather simplified toolkit and they find out 10 years down the road that what they did didn't have the impact which they expected? And I'm wondering how you handle that.
Is the micro? Yeah. So I think in the interest of time, we focus on the emulator-only part of the project, and the emulator is as good as the models that you're using to predict. At the same time, CLIMA, this Climate Modeling Alliance project that is partnered with this grand challenge, is instead taking the step of improving the accuracy of climate models. And the way we can do that is that we now have rich wealth of data from satellite floats in the ocean, vertical profiles and balloons in the atmosphere. And we don't use all that data to calibrate our models, largely because it's a very heavy computational task, and modern climate models, even state-of-the-art climate models, rely on old-fashioned architecture, CPUs that have limits on how fast they can run these models. So we have created a new model, a new climate modeling partnership with Caltech that is now running on GPUs. It's much faster, and then we can do this training using artificial intelligence techniques to actually train a model and improve its accuracy, at least against all available observation.
But actually, that's one of the reasons why we're doing the emulator project, to make this process faster. So we're only as good as the climate models we're trained on, but when you come to use information from climate models for something like estimating the flood risk of the MIT community, oftentimes you're using the 10-year-old climate models because that's when the scenarios were developed that and all of the climate information and the big ensembles of climate models that we have are reflecting the scientific knowledge of several years ago because of that big sort of infrastructure and need to process all that data. So if we can make that faster, then we can react more quickly when the climate models are improved and be able to feed that directly into decision-making rather than wait 5 to 10 years.
Just very quickly, I need to add that it's terribly important for all of us to convey not just our best estimate of these things, but the uncertainty, some estimate of uncertainty. And people who deal with risk on a day-by-day basis are used to having to make decisions under uncertainty. It's up to us to convey that uncertainty.
I was just going to question whether there was a possibility that policy and political scientists can be involved in this whole process, because one of the things I see in Boston, where I do a lot of volunteer work along the waterfront, is that flooding happens. I mean, this is not a future thing for Boston. We're seeing flooding every month during the winter. I have people whose homes have been almost flooded. It comes up to their next door neighbors. So, I mean, their homes are getting close to flooded. Streets are flooding. Lots of other things are. But it seems like the city is not really reacting to that very well. And I think you would think that some expert opinion would help that change, but it's not to be. And so I think there's like another lever that needs to be worked on. And we do have a political science department here, so I'm just wondering whether people have thought of bringing in those people to help figure out ways that it's most convincing.
Sorry, you can go first.
Okay, so I will say that our broad set of PIs really spans the entire MIT, including several of our collaborators who are involved in developing the climate and testing the climate interactive model in terms of how it speaks to communities. So we have that expertise sort of integrated within the broader team. I also did want to note that that Chris here, Chris Womack, our PhD student, is also a recent graduate of our technology and policy program.
And I'm from the School of Architecture and Planning, and so and we are working quite closely with the city of Boston. And I think the challenge is when it's private property, that the city has different levels of warnings and controls over new development, but when it's grandfathered in because it exists already, but it's slow movement because they have to go and negotiate with every owner. But part of our project also works with real estate developers, because currently, for example, East Boston, there's a lot of new development along the waterfront. Those expensive $100 million units can be raised up and protected, but then all the water goes through to the back of East Boston. And so we're trying to figure out with the city of Boston too, how they use their resiliency checklists and how we can really help new developments be more proactive and know that there are issues happening. And so there is work going on here, but I would love to connect to sort of understand what locations you're talking about specifically.
Great. There's one question here, and then one question in the back there, and then we'll close this session. It's Fred.
Hi, I have a question on hurricanes, so maybe this is Kerry's field. It seems to me that, more recently that the hurricanes in the Caribbean have become, more intense and higher level, at least they're reported that way. And also reported were very high temperatures in the Gulf of Mexico and off of Florida, I think way beyond what anybody had imagined would be happening. And so you sort of characterized extreme events as being rare, but doesn't this seem, aren't we seeing essentially more intense storms already, almost frequently, much more frequently? And I guess the second part of the question is, are these storms essentially, re-energizing themselves more aggressively than in the past as they, sort of go over land and then go over water and then go over land again. It seems like it's, the problem. I mean, if you look at the devastation in Florida, on the west coast of Florida, I don't think they'd seen anything like that in a very long time. And Puerto Rico's been, pretty much wiped out a couple of times. So, I'm just curious as to your view as to, what's really happening there now, and aren't we seeing the intensity now on a regular basis?
So we're hobbled in answering your question by poor records prior to about 1970. There's no question that almost every metric of Atlantic, it's 10% of the world in hurricanes, has gone up very rapidly since the mid-1980s. No question about it. We don't see that signal anywhere else. And the signal we're seeing is largely not a global warming signal, but it is a man-made signal. We're pretty convinced now, and there are a lot of papers from many different groups, that what we're seeing is a recovery from a man-made hurricane drought in the 1970s and 80s. How did we do that? Sulfate aerosols, which are, among other things, a byproduct of fossil fuel combustion. And when we ramped those up from the post-war period to the 70s, Atlantic hurricanes dropped, and there's a very interesting physics connecting those two. And when we passed the Clean Air Acts, sulfates went down almost as quickly and the hurricanes came back. Unfortunately, it's not being reported that way in a lot of the media.
And the last question in the back.
All right, I'll keep it quick. Do you think there are, or maybe should be, ethical concerns about producing climate-relevant knowledge with a granular level that might enable some actors to say, all right, we'll go build our emissions somewhere safer, or an insurer could decide, okay, well, we're going to stop insuring these people there because it's more risky. Do you think that could be a problem?
Well, you're not suggesting that we shouldn't provide granular information, I hope, for that information. But as I said before, it all has to be bounded by uncertainty. You can't pretend to be certain about that granular information anymore about the other. It's terribly important to convey that. How people use it is something that's also a kind of science I won't address, but maybe Noelle.
Yeah, I think what I would say to that is that, what we want to do with our project is make sure that the information is out there and accessible to all, that you don't need to have a highly paid consultant and a proprietary model in order to get the best available scientific projections of future climate. So we really view this as making it possible to empower those communities to make decisions on their own, rather than rely on those with power that have that information. So we're making everything sort of open source for those reasons.
All right. Let's thank our speakers once again. All of our speakers. The last session will look at the future of EAP. So if you want to know what the next 40 years hold, come back in 10 minutes and we'll get that last session started.